And then layout of gears. So this is look at here. Okay, so this is so we call gears. The gears they are driven by the torque. They are driven by the shaft. So we suppose we have the 4 gears here, and three for smaller gears and 1 bigger gears. So each of these gears they are driven by a shaft. Do you guys agree? Because all these gears they are mounted on the corresponding in the shaft. So the gears are this. When you have these multiple gears, the gears are arranged in a symmetric manner to eliminate the radial loads. Right? So you can see, and these are 3 guys, 3 little ones, and supposedly, and they should be technically sound. So these 3 guys need to be arranged about this one symmetrically. Why? Because if these 3 guys are arranged symmetrically, the radial force, you can see the radial force, this is the 3 smaller gears give to these bigger gears, 1, 2, 3, and these 3 guys can balance one another. So then the system will be statically the sum. So all this one, if you have 2 gears, I'll also make sure. So these 2 small gears and the radial force from here and the radial force from here, and these 2 guys they compensate each other also. So the turbines. So the turbines is a very, very big word. So you can see, so turbines, we have some, this is a gas, this is the combustion, this is a part of combustion. This is a gas, this is gas here. And so this is gas, this is coming out here. So look at it, this is inlet and outlet. So here, this one, okay, if you have inlet, go this way. And then all this gas will be going through this orifice and this orifice, and then you will have a thrust force. No, I'm sorry, it's axial force. It's axial force because you can see this profile and this profile. So the thrust force or this axial force, and you need to have some mechanism to balance this thrust force. To balance this is the axial force. Do you guys agree? Right, so you can see here this gas. I have gas here. This is the gas is fed from the top and bottom, and then so this gas will flow from this one to this way, and from this orifice this way. And so when this gas flow this way, and so this is a gas flowing and will generate this axial load, and to this is the turbine, right? And then finally. For this shaft, you must have some mechanism to balance this axial load. Otherwise, it will go in that way. So that means you need to have the extra additional this mechanism for balancing. However, if you have this kind of the configuration, that will be better. So this is my inlet. So this inlet, this gas, the gas will be fed this way, will be fed this way. So we have, for this is gas flow and this gas flow, and they generate this axial load to the right, to the left. For this gas flow and this gas flow, and they generate the axial load to the right. So these 2 thrust force, we call the thrust force, and these 2, the axial loads, will balance each other. And so you can see, this is the polar shaft, and you do not need to have this is extra mechanism. And to balance, to fix, this is a turbine system. You guys agree? It makes sense, right? Okay. And then we look at this one. Horizontal versus vertical shaft. That's because sometimes based on our needs, some shaft is oriented horizontally, some shaft is oriented vertically, or sometimes the shaft is oriented this is arbitrary this angle. So for horizontal shaft, the deflection due to gravity. Usually the shaft is made of material. Usually it is metallic material. So this has own self gravity, right? You guys agree? Even theoretically, even you do not do anything, you have a shaft. This is support, left support and right support. So sometimes, so because of gravity, this guy will deflect to some degree. And no matter how strong this material is, it will deflect. So this deflection, so this deflection due to the gravity results in eccentricity between the center of the rotation and the center of mass. So this is center of rotation, but the mass is a little bit going this way. So this is a deviation between these two things. So this may cause instability. So this is if the deflection is huge enough, so this will not stable while it runs. So on the contrary, for vertical shaft, okay, so you need a thrust bearing to take the gravity load. So if we orient this shaft this way, and you must have some mechanism to support the gravity. Otherwise, it's going down, right? Okay, so be very, very careful. So design procedure, and we are mechanical designers. So some guys are from aerospace engineering. So aerospace, they are aerospace engineers. We design things, and are we supposed to design for shaft? And we need to consider the strengths and whether it is strong enough or not. And we need to consider the stiffness. If it is strong enough or the stiff enough. And the strength and the stiff, they are two different concepts, right? The strong and being strong means that this guy does not break. However, being stiff means that this guy does not deflect too much. So they are two different concepts. Don't be confused, right? Okay, so additionally, because the shaft is usually rotating, and so it is at critical speed. So given a shaft, so you must tell the operators what is the natural frequency. No, I should not say natural frequency in singular form. I should say natural frequencies of this shaft, because for any system, supposedly this guy has multiple natural frequency, right? So usually this is times. This is a whole number of times of the basic frequency. We call the lowest one. We call lowest critical natural frequency. Can you write down it? The lowest natural frequency is called critical natural frequency. Whenever we talk about natural, this is a critical natural frequency. We are talking about the lowest. So, a mechanical designer, you must know that what is the natural frequency of your shaft, and then you tell the operator. Okay, why? Because supposedly, when anyone who wants to use this is your shaft, and this guy must make sure the applying frequency, the actual rotating frequency of your shaft must stay away from its natural frequency. Otherwise, what will happen, guys? Resonance, right? Resonance means that the applied frequency to the system is very too close to the natural frequency of the system, and then this system will break immediately. Okay, so then design for stiffness, and we talk about the design for stiffness. Why the stiffness is big? Because why the stiffness is very, very important? Because if the shaft deflects too much, okay, we have instability, and so you can see if we have the gears mounted on this shaft. However, if this shaft is not stiff enough, we have bigger deflection. So the shaft, these gears might not be able to mesh with the other gears. So the deflections should not cause mating gear teeth to separate more than about 0.005 inch, nor should they cause the relative slope of the gear axis to change more than about 0.03. So this should not deflect this way. Okay, if I have gears, gear 1, gear 2, if these two gears they are matching each other. So this is a gear. This deflection should not be more than 0.005 inch, and also the slope. The slope is this deflection I have some this deflection slope, deflection, this angle should not be more than 0.03 degree. So the shout deflection across the plane of this barium for the barium must be small compared to the thickness of the oil film. Usually because the shout is supported by this barium system and this barium system, right? So if this guy deflects too much, usually in order to minimize the friction, so in the barium system and in the interface between is a barium system and this is the shaft, and we apply some lubrication. We have lubrication C. If this deflection is huge and to penetrate the lubrication's film thickness, and the lubrication will lose the function. Okay? You understand, guys? So we will talk about the barium system later, but now we are talking about the shaft. The shaft angular deflection at a ball or roller barium should generally not exceed 0.04 unless the barium is self-aligning. And so this ball and roller barium, and also where this is very similar as here. If this is the deflection is bigger than 0.04 degree, and so your shaft is going to be varying, and it's going to be in contact with this is the barium system, roller barium system or barium system directly, and then this is it's much easier to be worn out for this is barium systems. So unless the barium is self-aligning, if the barium is self-aligning, this guy can automatically align and to adjust the angle to make sure your shaft, the shaft end will not penetrate, will not have direct contact to the barium system. So it's self-aligning. Questions regarding this slide? No question? No question. I'm talking about shaft design procedure. So this is so first we need to draw a free body diagram. And free body diagram, right? Free body diagram is that we focus on this is the atom of interest, and then we look at what kind of forces or moments, and so other neighboring atoms are exerting on this is the atom. And then in order for this guy to be in a state of equilibrium, and we must have the 3 force balance equations along with 3 moment balance equations. So these are free body diagram. So develop a free body diagram by replacing the various machine elements mounted on the shaft and by their statically equivalent load or the torque components. This is what I just told you guys. And in reality, we have so one component. This component is in contact with a lot of other components, and so we just idealize. We just throw away all other components. Just only focus on this element, and then look at for these other elements what kind of force or moment, and that is applied on this item. So to illustrate this figure shows 2 gears exerting force on shaft, and this is figure 11b shows a free body diagram of gears acting in the shaft. We can show you. So here, so this is the shaft, and we have 2 gears. So here, this gear has the pulling force P1. So this is gear has a pulling force P2. So you can see, we just remove this is the 2 gears, and we apply. So this is P1, right? So this is P1 here, and we have this torque because this force is applied is not at the center of the gear. And similarly for the gear 2, we have this force, and we also have this is a corresponding force under the corresponding torque because so this force is not applied at the center of the gear either. So definitely for this is support A and support B, and we have this is the support forces, reaction forces. So this is a movement diagram caused by the load in XZ direction. So this is XZ, this XZ direction. Movement diagram caused by the load in XY direction. XY direction is a horizontal in the plane. So this is torque, and torque only we only have torque between this gear and this gear. So outside this is the distance the interval between these two gears. So we don't have a torque. Questions? Questions regarding this one? So given a gearing system, given a shaft system, and you can just draw the free body diagram. Right? Okay, so this is our first step. And the second step, we know that the bending moment, the moment is the vector, right? You understand, guys? Moment is a vector, just like the force. That's a vector. Vector means that this guy has direction, not only this is magnitude. This guy has direction. Also, so if we have multiple moments, and we also if we know the directions of these multiple moments, and because we know they are vectors, so we can just get a resultant the moment using this equation. If so, these two moment components, they are orthogonal to each other. Yeah, these two guys, they are orthogonal, right? Because x, y, z, they are three. This is orthogonal axis. You understand, guys? So this is our resultant. This is a moment, and the reason we can use this equation is that we know mxy and mxz, they are perpendicular to each other. That's the only reason we can use. Otherwise, that's another story. We use parallelogram. It's a theorem to get it. So then develop a torque, this moment, torque diagram, and torque developed from one power transmitting element must balance the torque from other power transmitting elements. Establish the location of the critical cross section or the X locations where the torque and moments are the largest. And for ductile material, we use MSST and DET and cover in this one. So we already learned this MSST. MSST is also named the Tresca theorem, Tresca criteria, and DET is also named. This is Lomises. This is a criteria. For brittle material, we have other this series. We did not talk about it, but I give you the slides, right? So if there's a need, you can come and to the slides I give you and to know the equation. Any questions regarding this slide? We are going to focus on the DET and MSST for ductile material. Questions? No question? No question? Move on to the next one. This one we talked about already. How to get this free body diagram. So be very, very careful. This is the first step. And if you mess, this is a free body diagram. The free body diagram is the first step in the darkness, right? And you will totally get lost. that means if you get lost and come back to check your free body diagram. If you, no matter how you try, the answers are ridiculous, come back to see the free body diagram. Usually the free body diagram and cause a bigger trouble. So this is example. So here you can see the gear and this is a gear, this is a chain. So this is a bearing, and so this can rotate. And so these two guys are connected together, and we have a bending moment, and so this is a bending moment. So here is to the free body diagram. This is a free body diagram. This is a system, and then we just based on geometry and the loading conditions, and we can have this free body diagram. Then we get this moment diagram and also this torque diagram. And then we talk about how to use this MSST and this is Soderberger. And people use the Soderberger, but I told you this Goodman theory, right? Goodman, this criteria. It doesn't matter. We have. I give you all these tools. right? I give you all these tools. So you can see if we combine the IMSST and the Ford program criteria, and I have two equations. So this equation shows that if you have all these parameters, Sy is yield strength, Se is the actual endurance limit, and Kf is the dynamic stress intensity factor. M mean is the mean moment. Ma is alternating moment. The same thing for T. Tm is the mean torque. Ta is the alternating torque. And Sy is the same. And so this is if you have a D, okay? If you have the diameter, D is the diameter of your system, of your shaft. If you have the D already, and you can use this equation to calculate the safety factor. I want you guys to write down. I will not give you example today. I'm doing example later, but I want you guys to know what this is letters stand for. So one more time, okay? So when should we use this equation? And we should use this equation if we know the diameter of the shaft, and we want to see and what is the safety factor I can have. So then you use the first equation. However, so if I know the safety factor, I want to know what kind of the diameter I should have. And I then actually use this equation. Right? Okay. So yeah, this equation, you can just manually to see if they are interchangeable with each other. But which one should we use depending upon which value is the known value and which value is resolvable. Okay? So this is if we use combine the MSST and Soderberg criteria. And Soderberg criteria is used for this is if the alternating value is non-zero. Soderberg. So this is the first one. So secondly, MSST is for the ductile material, and Soderberg criteria is for the second. And so this is a combination because I know, and this is the shaft is rotating. That's the reason we have mean moment, mean torque, and alternating moment and alternating torque. So this is the first combination of MSST and Soderberg criteria. And then if we want to use DT and Soderberg, and we have another two corresponding equations. One more time. So this equation is applicable if, and we already know the diameter of my shaft. I want to determine how big the safety factor is, because the safety factor is usually needs to be greater than 1.0. And the second equation gives us the direction that if we know the desired safety factor and what kind of factor I should have, because we are mechanical engineer and based on the needs from the customers, and we need to give people the material, what kind of material should we use? What kind of geometry of the shaft should we have? Right? We are designing things. So here is Goodman's theory, Vomices. If we combine Vomices, this DT, okay, DT, and this is a Goodman's theory together, and we have these two equations. So this is N, safety factor, so this is the D. So DE, so here, so this is because this textbook and they give us a very comprehensive these combinations. This is for DET theory, the Vomices theory, along with our Gerber one. Right? So this is Vomices, Goodman. So this is DE Gerber. I told you Gerber is very good, right? Whenever I hear Gerber, I always see the baby in the photo. Baby food, right? Bigfoot, so Gerber, this one is very lovely, but it is quadratic. It's mathematically it's not user friendly. So, but still, the textbook give us so this two equations. N is a safety factor, D is a diameter, and you want that. So this here, that is another one. D along with ASME elliptic, ASM